So we're talking about acids. If we think about an acid, I know that some of you could come up with properties that an acid has. So maybe reactions that an acid could participate in, or something that I could measure about an acid. So, does anyone know or remember some properties of acids in general, whether they're strong or weak? Okay, and what's the taste? That was a lot of different words. Tangy, I like that one. Tangy. Usually we would say sour taste. The bitter taste is a base. Sour taste is an acid. Although I might just say tangy from now on because that's how I would describe it too. Anyone else remember something that we could actually test in the lab? Because of course I will never ask you to taste something, even though he's right. Yes? So it reacts with magnesium or maybe zinc or some other reactive metal. So you could put magnesium, you could put zinc. I'm going to bet that in Chem30, someone put a piece of magnesium in a strong and a weak acid so you could see which one bubbled more. Yes? Conductive. So if you think about acids, and the same will be true for bases, there are ions present in an acid or a base solution, so they conduct electricity. Anybody else? Yeah? Oh, look at us being specific here. pOH above 7 and conversely pH less than 7. Maybe one more? Yeah? Yeah, we'll put that up here. That's a base. Bases feel slippery. There's probably one more thing that I think that you should know. Maybe something about a color that something turns. There we go. Blue litmus turns red. These are all things that you hopefully have heard about acids at some point previously. Now, if we consider a strong acid versus a weak acid, the difference will be in how strongly they display some of these properties. The difference is based on percent ionization. Now, if I have a strong acid versus a weak acid, strong acids ionize completely, whereas weak acids only partially ionize. So if I look at these properties, yes, a strong and a weak acid would both display these, but the strong acid would display them more. So the taste would be more sour, it would be more conductive, the pH would be even lower than 7, or even the pOH would be even higher than 7. So strong and weak acids both display these properties, but strong acids display properties more. So same properties, but you just get more. Now, we could compare a strong and a weak acid. If we compare HCl, which is a strong acid, now let's say I didn't tell you that HCl was a strong acid. Is there a way that you would know that it's strong? The data booklet, there's that gray line, you would look above it, those are all strong acids. CH3COH, which is acetic or ethanoic acid. It's ethanoic acid because if you look at its structure, it's a carboxylic acid. It has 2 carbons, so ethane, and it has the COOH, so oic acid. Both of these are acids. But if I look at the difference between HCl. HCl, notice, it's basically a 100% reaction. We're saying the percent reaction is 100 or really close to 100, where all of the HCl will completely ionize in water, so that if I start out with some HCl, I will have none of it left at the end. It will completely 100% become products. Remember that this is a quantitative reaction, so there's no equilibrium. That means strong acids are not super interesting for us in this unit on equilibrium because there is none. This is not going to be an equilibrium system because there's not going to be a point where I have reactants and products present at the same time. Now, if I consider my acetic or my ethanoic acid, here's the percent ionization. So we're saying over here, the percent reaction, like we calculated before in lesson 2, would be less than 1%. So I put my acetic acid in water, less than 1% of it ionizes, and then I get to a point where I'm at equilibrium. I know I'm at equilibrium for a couple of reasons. One, it wasn't a 100% reaction, but two, I got the double arrow showing me that some of the reactant is becoming product and some of the product is becoming reactant. Now, if I started with the same initial concentration of both of them, so let's say that I had 1.00 moles per liter as my initial concentration for both of these acids, and I let the system complete or get to equilibrium. When I get to equilibrium, or in this case, I'm going to say this is the end of the reaction, I would have no HCl left, but I would have 1 mole per liter of hydronium. So we're saying in the first reaction, all of it, every bit of that initial concentration of HCl became hydronium. In the second example, even if I start with the same concentration, 1 mole per liter, if I look at equilibrium, I am not going to have 1 mole per liter. I'm going to have, over here for hydronium, 4.24 times 10 to the power of negative 3 moles per liter. Will I have 0 of my acetic acid? I won't. I'll have just a little bit less. I will have 1 minus 0.00424 moles per liter. Notice how I'm subtracting such a small number that essentially I would be rounding my answer up to 1 mole per liter. So even though I'm using some, it doesn't really look like I've used any there. Now, if I calculated the pH of both of these solutions, remember that pH is based on this. We saw that in our last lesson. So, in the first reaction where I have a strong acid, the pH would be significantly lower because the concentration of hydronium is significantly higher. Here's my hydronium. I would do the same calculation, but of course, because the concentration of hydronium is lower, the pH is higher. So the way we can explain the difference in pH values is because of how much hydronium is actually present. In other words, whether we had a quantitative reaction or whether we were at an equilibrium. Now, does anyone want to ask a question about this? Realistically, this is a theory question where you might not even have to calculate something. You would just have to explain why there's a difference. Oh, it would be the same. So over here, we would have 1 mole per liter of those ions as well. The general rule is if things had the same coefficient in a quantitative reaction, they should have the same concentration. Did anyone else want to ask anything here? Okay. So if we think about acids and bases, we could do some calculations based on this idea of percent ionization. So we could think about this solution of nitrous acid. Now some of you might say, oh man, we have to know these rules for naming acids again. Kind of, but not really, because in your data booklet they're all listed anyways. So if you forgot that nitrous acid is NO2, which is the nitrite ion, but with hydrogen attached to it, you could look up HNO2. Now we have a solution of nitrous acid. So I'm just going to write out the reaction that would go along with this acid. Anytime you have a solution of an acid, you always have the acid and water. Because nitrous acid is not a strong acid, it's a weak acid, I'm putting the equilibrium arrow instead of the quantitative arrow. The products would always be hydronium and this little guy. It's what's left after I take the hydrogen away from the acid in my reaction. This is generally a base that's left over because I just took the hydrogen away from it. Now it says the pH is 1.13. Now I wrote the pH over here because I know pH is related to the concentration of hydronium. So the first thing I'm going to do is figure out the concentration of hydronium by doing 10 to the negative pH, or 10 to the exponent of negative 1.13. So if you're given the pH, you can use that to find the concentration of hydronium. Given the concentration of hydronium, 0.0741 moles per liter. Now this particular value, I'm not rounding off to the correct number of significant digits yet because I'm not done figuring out my answer to the question. And I'll just remind you that you should never round unless you are finished calculating. If it's your final answer, then yes, round it. At any other point in the question, if you're still calculating things, don't round numbers until you're at the very end. Now, that's the concentration of hydronium. It said that I had 1 mole per liter of nitrous acid. So we're looking for percent ionization. Percent ionization is basically percent reaction, but we changed the name because it's about an acid specifically. Percent reaction is where we compare how much product I got to how much I could have gotten if the reaction was quantitative. If the reaction was quantitative, like with a strong acid, I should have had 1 mole per liter of hydronium, but I didn't. So my percent reaction, or in this case, percent ionization, would be 0.0741 moles per liter divided by the 1 mole per liter that I could have gotten if this reaction were quantitative. So I know my percent is 7.4, and I would round it to 2 significant digits because there were 2 significant digits in my pH value. I know it looks like there are 3, but remember in pH values, it's only what comes after the decimal place that counts. Now, sometimes you might just have to use this idea that not all of an acid ionizes when it's not strong, but a lot of the time we'll have to go a little bit further and we'll have to consider something called Ka. What is Ka? It's just Kc, but for acids. Just like Kw was Kc, but for water. It's the same thing. I love how excited you guys are about all these different K values. Let's say that you were like, oh man, do I have to know all these K values? Oh, look, there's a whole list of them in my data booklet where for acids it tells me the Ka value for quite a few of them. So, essentially, what we're calculating here is the acid ionization constant. It's a value of K for the acid ionization reaction. So remember, K is just an equilibrium constant. Specifically, we're talking about acid ionization equilibrium, but it's just equilibrium. It's the same rules. So it's the acid ionization constant. That's what Ka is. It's there to tell us the extent of an acid's ionization. If Ka is larger, then the acid is stronger. So in your data booklet, you'll see that they're not in alphabetical order. They're in order based on these numbers. There are bigger numbers near the top and smaller numbers as you go down. This table is set up just like the redox table. On the left, strongest things are at the top, in this case, acids. On the right, strongest things are on the bottom, in this case, bases. Same setup as the redox table, which I think is very nice that they set it up the same way. Now, complete ionization happens when you have a strong acid, and like we said before, it's quantitative. That's why in your data booklet, instead of giving you a value for Ka, it just says very large. We don't even give you a number because we assume it's either 100% or close to 100%, and there's no point in talking about equilibrium. Weak acids have a limited ionization. That's why they're listed in the table, and that's why we actually care about them in terms of equilibrium. So we will actually focus on weak acids because they actually have equilibrium systems and strong acids don't. So if we look at any weak acid's ionization, there's the acid, there's water, there's hydronium, and like I showed you before, there's the base. Now, I represented things in general here with A representing any base that could exist. Take a look at the Ka expression. It follows the same rules as Kc. You put the products on top, and if anything is a pure liquid, like it is here, you do not include it in the K expression. So, even though water is one of the reactants, I am not including it in my K expression. Now, what else do we know? Look at these two things. It looks like they have the same coefficient. So in a lot of cases, these two have the same value. There will not be many cases where the concentration of hydronium and the concentration of the base that's produced as a result of the acid ionizing don't have the same concentration. In most cases they will, and you can assume that they're the same number. Now, does anyone want to ask anything there? So we can use the Ka value to predict some numbers. So if we consider first benzoic acid. Benzoic acid you can find in your data booklet. You don't necessarily need to write down the reaction and the formula all the time, but I'm just going to start by doing that here. So that's benzoic acid. When it reacts with water, I get hydronium, and in this case, C6H12. C6H5COO negative. Now, maybe you're saying to yourself, how would I have known that? How would I have known that C6H5COO negative is the thing that I get? Well, remember, you're always taking a hydrogen away from the acid when you make the products. And if you look in your data booklet, it shows you for every acid in there, the acid and the conjugate base, so the thing that you get. So if you don't know, maybe check there, but all you're doing is moving a hydrogen. Now it says that in the question, I'm starting out with 1 mole per liter benzoic acid. That's the initial concentration here. Now, if I bring us back to sort of the first lesson where we looked at ice tables, remember in the previous example when we looked at ethanoic acid, I said it was going to change, but by so little that it was going to be essentially the same as it was before. So this change is going to be minus x, but x is so incredibly small because it's a weak acid. It doesn't ionize very much, that at equilibrium, we will have essentially 1 mole per liter. It'll be 1 mole per liter minus 0.0000 something, but when I round it, it's going to be the same number. When I consider these two, they both start at 0 because I don't have any until I make my solution. And I'm going to increase their concentration by x, but it's a weak acid. The change, or the percent ionization, is so incredibly small that these two values will both be very small. I don't know what they are yet, right, because this is part of what I'm calculating is the concentration of hydronium. And if I just use an ice table, you'll see I'm going to get 0 as my answer. I'm not going to get an actual value, so I need to use my K. What I do know is that these two numbers should be the same, right? They have the same coefficient. They changed by the same amount in my ice table. If I calculate them, they should be the same value. So I set up my Ka expression. Now, if you ever take chemistry in the future, this approximation that we did here, you might not be able to do it anymore. But for all of the examples we will ever do in Chem 30, we are assuming that the initial and equilibrium concentration of a weak acid is essentially the same value. You could use the quadratic formula that if you've taken math you would have learned about already and figure out exactly what it is, but you don't have to. And so I'm going to suggest that because you don't have to, and that the approximation is always valid in Chem 30, that you just use the approximation because it's way simpler. Now, I can look up Ka in my data booklet, so I will. Ka for benzoic acid is 6.3 times 10 to the power of negative 5. So I already know Ka, it's not what I'm trying to calculate. Now I just said that the concentration of hydronium and of my benzoate ion should be the same. If I represent them both by x, I would have x times x, right? So x squared, because I'm saying this is x and this is x. On the bottom, I know that I have 1 mole per liter because that was the concentration of my acid. So when I'm thinking about those equilibrium concentrations, if I want to find the value of x, I'm going to take the square root of 6.3 times 10 to the power of negative 5 times 1 mole per liter. So to manipulate that, I multiplied both sides by 1 mole per liter and then square rooted to get rid of the power of 2. You should end up with x is 0.0079 moles per liter. Now, what did I say X was? Well, it was the concentration of hydronium and or the concentration of that ion. Hydronium is really what I'm after, right? Because it told me to calculate this. So I can say that that's the concentration of hydronium. Then, because now I know hydronium, I can calculate the pH. pH is negative log concentration of hydronium. It's really important that you know that the concentration of hydronium and the concentration of the acid probably aren't the same. If I was a person who was making a diploma, I wouldn't ask you to calculate the pH of a strong acid because you don't have to do any work. Negative log of the number, boom, you're done. There's nothing to it. If we ask you to calculate the pH of a solution of an acid, it's a weak acid, and you got to do this. You got to go through the steps and find the concentration with the K value. So here, negative log of our 0.0079 moles per liter tells us that the pH is 2.10. So here are my two answers using my Ka value. Now, does anyone want to ask anything about that example? This is a pretty typical question. We give you the concentration of a weak acid, and we ask you to find the pH. Now, we could do the same thing for carbonic acid. The approximation is listed here just so that you are clear on why we are using that same value. Since the difference that we'll use is greater than 1,000 in basically every case, we can always assume that this approximation is true. The second example is basically the same as the first example. So why don't you all give it a try? You're going to go through the same steps that I went through in the first one, but this time with carbonic acid instead of benzoic.